whether it was skewed. And it was a pretty simple arithmetic operation because it simply required us finding the center point and then coming back and finding the center point of each of those pieces, or the quarter points. So it wasn't a real difficult operation. But it's also not the most reliable because it talks about the number of people, and it can still be subjected to outlier values or values that are clustering in different areas. So there's other ways to be able to look at distributions, and we're not going to get into drawing graphs of those things very much, but we need to be aware of the basic concept of this type of a distribution. Some distributions can be skewed to the left, indicating that they got an excessively small value somewhere and it pulls the mean that way. Some can be skewed to the right, which means there's an excessively large value and it could get pulled to the right. Some don't have any kind of a semblance of order at all, which is a nightmare, but a different type of study that we have to do in statistics. And then a vast majority of the things that happen in the real world turn out to be what we call symmetric distributions, or a normal distribution, also known as a bell-shaped curve. Now, you're not going to draw graphs of bar graphs like this, and you're probably not going to be looking at what the curve is, but the curve gives us an idea about what we're thinking with in terms of a normal distribution. Normal distribution is a specialized type of situation. It has special sets of rules and special sets of techniques that we can't apply if we don't know it's a normal distribution. But if we know it's a normal distribution, then life is good. Okay? So we refer to this section that we're talking about right now as normal distributions. If that's the case, then we expect to have, we expect certain things about a distribution. Number one, if a distribution is symmetric or normal, then we expect that the mean, the median, so take one of these sheets and pass it back, it's going to be useful for you for drawing a picture. You don't have to be able to draw this picture, but we're going to be taking some notes on here as well. In a symmetric distribution, if it's perfect, and not all things are perfect, but the more data we get, the more they begin to become closer to being perfect. If it's perfect, the mean, the median, and the mode, all three measures of central tendency stack up right on top of one another. Because the median, the mean, and the mode stack up on top of one another, it gives us a symmetric relationship. That's why we call it a symmetric relationship. 50% of the data on one side of the graph, 50% on the other side of the graph, if it's perfect. There are other characteristics of this graph that we could investigate if we wanted to do Math 241 in another semester. And if some of you do take Math 241, that will take you down this garden path a little bit farther. We'll do a little bit more investigation. But basically, that's all we need to worry about, is that we've got a nice symmetric curve that sits out here. And as a nice symmetric curve, then things are good. Now, what happens in that curve is that we run into some issues. We start running into the special features. You're going to see in this section several references to something called the 68, 95, 99.7 rule. We did not just make up those numbers, 68, 95, 99.7. A greater in-depth investigation of this would require calculus. I'm not teaching you calculus, but it would explain to you where we came up with those values of 68, 95, and 99.7. Normal distributions take all the work that we've done before with the concepts of mean and standard deviation and puts them together. So we need to talk a little bit more about a standard deviation. We know a standard deviation talks about the average spread, the average difference of any observed value from the mean. And this 68, 95, 99.7 rule talks about what happens when we start getting clusters of standard movements in the problem. You have to think of a standard deviation in the following way. The standard deviation is called a standard sized step. Do we all have a standard sized step? If I took 3 people up here to the front of the room and told them I wanted each of them to take 4 steps forward, would we probably see them counting? 1, 2, 3, 4. So we verified that they all took 4 steps, right? Well, they all end up at the same place. Why not?
Bigger feet.
Some people take bigger steps than other steps, okay? So in a normal distribution, you actually are going to have 2 scales going on your horizontal axis. One of them is the standard scale, which talks about the number of steps that they take. But like a ruler where you've got English on one side and metric on the other side talks about the distance that you cover. So in every normal distribution exercise, they have to tell you what the mean value is and what the standard deviation value is. And then they're going to start asking you all kinds of questions about standard deviations. If you take 1 standard size step above and 1 standard size step below, then between these values, you're going to find that you have 68% of all of the observations that are part of that data set. That number comes from calculus. We're not teaching the calculus. You just have to trust me. It's 68% is the nicest whole number for that. If we take 2 standard steps above or below the mean, inside this area, we consider to have 95% of all of the data that we've dealt with. This is what we consider to be expected values. Anything beyond 2 standard deviations begins to be something we say, ooh, that caught me by surprise, I wasn't expecting that. Similar to an outlier when we talked about the 5-number summary. It's not considered an outlier in the same context as the stage, but it's now the value that we're considering to be, that's unusual. I wasn't expecting that. If we take 3 standard steps away, then we've captured 99.7% of the data. Theoretically, it's impossible for us to ever get all of the data encapsulated because we're not going to get responses from everyone. So when you look at this curve, it does look like the curve comes down and actually touches the axis. The curve does not actually touch the axis. It just gets closer to it. It always leaves space available as we move along. So on these extremities that are sitting out here, beyond 3 standard deviations, to above and below, we still have 0.3% of the entire population out there that's split equally. Now that's what it means when it says we're looking at the 68, 95, 99.7 rule. And what we need to do then is to kind of do a physical example of that. So in here I want to insert a blank page, and I am going to put in that standard graphic that I'm going to use now, so I have to actually insert